Right. So October, November, paper 2, variant 1. October, November 2024, paper 2, variant 1. And you have to answer all of the questions, so there's no choice. Just like in traditional exams, you get a choice, you don't get a choice, right? A trolley of
Okay.
mass 0.2 kilograms is at rest on a frictionless surface. The friction is surfaceless, so the surface is frictionless. The surface is frictionless, and a block of wood is attached to the trolley. So here's the block of wood which is attached to the trolley. Block of wood attached to the trolley. The volume of the block of wood is 0.0012 meter cube, and the density of the wood is 650 kilogram per meter cube. So I hope these units are consistent. This is meter, so you don't need to change any units. Well, the first thing you have to do over here is calculate the combined mass of the trolley and the block. So what's the mass of the trolley? I think the mass of the trolley is, we know the mass of the trolley is 0.2. So mass of the trolley plus mass of the block, right? Mass of the trolley is 0.2. You need to worry about that. Plus mass of the block. Now, we do not exactly know the mass of the block, but we know the volume, but we know its volume and density. How do we calculate mass? We know that density is equal to mass per unit volume. From here, you can calculate the mass by multiplying the density and the volume. So that's what I'll do here. I have the density. I'll take the density. 650. I don't need to change the units because the units are already consistent. And the volume is already given, 0.0012. If I do the math on this one, I'll get my volume. Can you real quick do the math and tell me the volume?
0.78.
Come, I think you should get 0.78. 0.78. Okay.
Yes,
So
sir.
0.78 plus 0.92, this would be 0.78. 0.78 plus 0.2, so it will be altogether 0.98.
0.9. Yes, sir.
All right. Next question. Figure 1.1 shows student attaches a spring of spring constant 14 Newton per meter, which means what does spring constant tell you? Spring constant tells you that in order to show displacement of 1 meters, you need to attach a load of 14 newtons. 14 newtons per meter to the front of the trolley. So I attached a spring over here. The student holds a trolley. Uh, Student holds the trolley and the stretches holds the trolley and block and stretches the spring. Okay. So the spring is stretched. He releases the trolley and the block, and the trolley and the block accelerate from the rest. As the trolley and so he stretches, first pulls it back so that the spring is stretched, and then once he releases it, the trolley and the block accelerate towards the spring. Again, of course, eventually they will engage in a vibratory motion where they will move back and forth for a while.
Yes,
As
sir.
the trolley and the block accelerate, the student keeps the extension of the spring at 0.35. Calculate the spring. So the extension is 0.35. Calculate the force exerted by the spring on the trolley, right? So from Hooke's law, we know that if you stretch something, basically force is, I think I told you in when we were doing the MCQs as well, force is proportional to displacement, and force is equal to K times X. K is the constant of proportionality, and that is the spring constant. Okay, and X is
Yes,
the, over here, X is the displacement.
displacement.
X is the displacement. So in order to calculate the force, you need the displacement and the spring constant. You need spring constant and displacement, right? So I'll put the formula F equals Kx. We know the value of K, which is the spring constant. I think it was given above 14. So 14 is the spring constant, right? I think newtons are also meters, sorry, the units are also consistent. There's meters and there's meters and there's Newton. So I could just not write the units. It was fine. And X is the extension. How much is the extension? It's 0.035. 0.035. If you multiply the both, can you tell what you're getting? I think you should get 0.49 newtons. So that's the force that is exerted by the spring on the trolley. Okay, this is given by Hooke's law. The name is Hooke's law. Okay.
Mm.
Right. The trolley and the block are pulled at a distance of 0.86 meters by the spring. Calculate the work done by the trolley. So this is a formula for the work done. Formula for work done is force times displacement.
Mm.
We know this, right? Work done is equal to force multiplied by displacement. So we got the force 0.89, and this is the displacement. How much is the displacement? The trolley and the block and the pulled at a distance of 0.86 meters by the spring. So for force, I'm going to put 0.49, and for displacement, I'm going to put 0.86. Okay, and everything, the units are also consistent. So I am going to get 0.42 from here. Let me also
Four
double check
two.
for my calculator. Yes, it is.
Yes, sir. 0.42.
Okay. All right. Let's move forward. Okay, explain why the power transfer to the trolley and the block increases as the speed increases. What do you think? What happens if you increase the speed? Okay, what is the formula for speed? We know that momentary speed is equal to displacement over time, distance over time. So as the speed increases, distance moved also increases, right? So as the distance increases,
Mm.
work done also increases. And if the work done also
Mm.
increases, the power transferred also increases, because we know that power is equal to work done over time. So as the
Mm.
display, I'll just put in the, I'm not going to put in the entire answer. I'll just put in the chain of argument. So as the distance increases, the as the velocity actually, as the velocity increases, well, then I said let them speed increases, it leads to the distance, increase in distance, which leads into, because we know that work done is equal to force multiplied by
Four.
distance.
Yes, sir.
Work done increases, and if the work done increases, of course, if the work done increases, the power also increases.
I agree.
Power transfer also increases. I think you can convert this into a sentence, into an argument. That shouldn't be a problem.
Mm.
Okay, next. All right, on to the next question. A student makes a balloon, a ball from a modeling clay. A ball has a mass of 0.2 kilograms, in other words, 200 grams. She drops a ball from a height of 40 meters from the ground. Calculate the initial gravitational potential energy of the ball. So if the ball is placed at a height of 40 meters, at the top, the gravitational potential energy is equal to mgh. So the mass is zero point 0.2. This is the height. Gravitational potential energy is equal to mgh. Mass is 0.2, gravity is 9.8, and height is 40. So can you work it out? It should be simple.
Mm. Yes, sir.
Altogether, it should be 78 joules. Okay? Let's look at the next one. Calculate the speed of the ball immediately before the ball hits the ground. Ignore the effect of the air resistance. So now we know that once the ball goes down, right? The ball is coming down from here. There is a transfer of gravitational potential energy into kinetic energy, because kinetic energy of a body is due to motion, right? So there is an energy transfer. Just as the ball reaches the ground, all of the gravitational potential energy would have converted into kinetic energy, right? Because the ball is almost to hit the ground. So I'll say loss in gravitational potential energy is equal to gain in kinetic energy, right? So all of the kinetic energy it is lost, right? So the loss in gravitational potential energy is 78 joules, and gain in kinetic energy, we know that the formula for kinetic energy is half mv squared, and we know the mass as well, so we can work around. We have to know the you need to know the value of velocity. I don't think it should be difficult now. This will be 2 multiplied by okay, 2 multiplied by 78 divided by 2 multiplied by 78 divided by mass. Mass is zero point 0.2 is equal to v squared. Once you calculate it, once you square root it, let me know what you get. I think for the value of velocity, you should get 28 meter per second. Let me also double check.
Yes, sir. It's 28 meters
It's
per second.
28? Good. 78 multiplied by 2 divided by 0.2 is 80. Square root of 70.
It's actually 27.9, but rounded off, it's 28 meters per second.
I'm sorry,
I said it's 27.9, but rounded off, it's 28
rounded off
meters
to
per second.
28 exactly. There we go. When the ball hits the ground, it stops moving. The kinetic energy of the ball is transferred to internal energy, right? So we follow the transfer of energy. Initially, we had gravitational potential energy that is transferred into kinetic energy, and all the kinetic energy transferred now into the internal energy. Okay. The temperature of the ball, of course, when the internal energy rises, so does the temperature of the body. The specific heat capacity of the modeling clay is 1400 joule per kilogram degree centigrade. Calculate the maximum possible temperature increase of the ball, show your working. So the maximum possible temperature will be when all of the internal energy is converted into heat energy. Right? All of the energy is used to increase the temperature, right? So how much was the energy transfer? I think it was altogether 78 joules. And we know is equal to Q is equal to MC delta T. So we need to we're
Mhm.
looking for temperature increase, which means this is what we're looking for. We're looking for delta T. Okay. And the rest we know, we could just put in. So the amount of heat energy, this is the heat energy, which was previously the kinetic energy, which was previously the gravitational potential energy. Then it was converted into kinetic energy, and the same energy was then converted into internal energy. So it's essentially the same thing. 78 equals mass is 0.2, I think. C is 1400. 1400 times delta T, right? So I think delta T, which is the increase in temperature, should be equal to 78 divided by 0.2 times 1400. Before doing any of that, I mean, I'm doing it a little hastily, but before doing that, I think you should make sure that your units are consistent. So there's joules, there's kilograms, everything is in kilograms and joules and newtons. So
Yes, sir.
what should you get? I think you should get 0.8, 0.28. Please ask what the answer says. Let me also double check. So I'm going to put on my calculator. Actually do it on the screen. 78 divided by zero point 0.2 multiplied by 1400. So I am getting 0.2. That is right. Let me actually take a picture and put it on the screen. Yeah. Oh, what? No. This. Yeah. 0.27, you can say it's almost 0.28. You round it off to two. If you round it off to two decimal places, it's 0.28 degrees centigrade is the raise. Acha. Explain this. This is what we calculated. What we did over here is the maximal possible temperature, maximum possible temperature increase, assuming that all of the energy is converted, all of the energy is used in raising the temperature of the body, right? But is that true?
Mm.
This is true in the ideal case, right? Ideally, what happens when there is a very smooth, very perfect energy transfer, but this is not what happens in the real life. In real life,
Yeah.
a lot of energy is lost. Okay, so the increase in temperature will be, this is the ideal increase in temperature, right? If all of the energy is transferred, if no energy is lost. But we know energy does get lost in between these processes. So suggest one reason why question B part 2 says, suggest one reason why the actual temperature increase of the ball may be smaller than the value calculated. Well, because the heat is, a lot of heat is, some of the thermal energy is transferred to the ground or lost in the surroundings. Some thermal energy is lost in the surroundings. Okay, I hope it makes sense. All right, all hands
Mm.
on the next question. Interesting. Figure 3.1. Figure 3.1 shows gas at room temperature. The gas is trapped in a metal cylinder by a metal piston. The metal cylinder is immersed in a, the gas is trapped in a metal cylinder by a metal piston in a fixed position. So this position is fixed. The
Okay.
gas is immersed in a boiling water. So everything, the metal cylinder along with the piston, everything is immersed in boiling water. And the temperature of the trapped gas increases. Explain in terms of electrons and the atoms of the metal how thermal energy is transferred through the walls of the metal cylinder. I hope you remember this. This is a big container, right, of boiling water. Okay. And if you place the metal container along with its piston, what happens is that this water heats up the metal surface. Now it's a metal, right? And the metal has actually, we'll draw thick metal,
Yes.
something like this. Okay. Now this is metal. Okay. And if it's placed in a boiling water, what happens is the the boiling water heats up the surface of the metal, one end of the metal, right? But how is heat transferred from one surface of the metal onto the from the outer surface onto the inner surface? This is where conduction comes in. You remember the conduction where you have, I mean, it's already giving a lot of hints to read. Thermal energy transferred through the wall in terms of electrons, the atoms of the metal. We know these atoms are free electrons. So when the outer, I'll actually try to put a step-by-step argument over here. When the boiling water hits the outer surface of the metal, it heats up the electrons. Electrons gain energy. They start moving across the metal crazily because electrons are free. There's no one to stop them. So
Yes, sir.
the electrons keep on passing on to the energy to the protons as well as other electrons. And energy is very quickly transferred onto the inner layer of the metal. And this heats up the gas as well because gas particles are constantly colliding. There are gas particles inside, right, which are constantly colliding with the surface. I mean, they're colliding with themselves as well. They're also colliding with the surface of the metal. So they also get heated up. And eventually, the temperature of the gas rises. Interesting. So let's follow. I'm not going to write the answer for this. I hope you can. I'll just help you to follow the transfer of heat. So the heat is transferred from the water molecules because the water molecules are already boiling, from water molecules to the outer surface electrons of metal. Okay, and the heat reaches the inner surface through conduction, right? The heat reaches the inner surface of the electrons through conduction. This is where the conduction comes in. Okay, I'm writing down in the form of a mind map. I hope you can frame sentences from this. So inner surface, from the inner surface, to the gas particles, right? Because the gas particles are constantly colliding. So there's a Brownian motion. So there's a Brownian motion of the gas particles. The gas particles are constantly colliding with the inner surface. So this is how the gas particles get heated up. And the gas particles, the temperature rises. The temp of gas rises. Okay, I hope that gives you enough idea about question two. Okay, let's call it today for today. And we've almost run out of time as well. To
Yes, sir.
pick it up from here tomorrow. Thank you
Yes, sir.
yourself, and we'll see you tomorrow. Bye-bye.
Yes, okay.
Part B of the question says the piston is fixed in a position. So if you look back at this, we keep the position of the piston fixed somehow. Maybe we're pressing it, or maybe we somehow find a way to keep the piston fixed. Okay, the piston is not moving either this way or this way, neither this way nor this way. The piston remains fixed at this place. So if you could find a way to fix the piston, the piston is fixed in a position. So the pressure of the gas increases as the temperature of the gas increases. It makes sense, right? Because look, here is the case inside. और आपने piston को you fix the position of the piston. Let's suppose this is the position of the piston, right? Now, as you're heating up the gas particles are colliding the walls more and more vigorously. So as they're colliding the particles with more and more force, I will say the pressure of the gas definitely increases, right? So I think this is a pretty simple question. State what happens to the motion of the particles as the temperature increases. What do you think happens to the motion of the particles as the temperature increases? The particles, or I would say the average speed of the particles increases. So the speed of the particles, I just write their speed increases. We can also say their average speed increases because on average the particles are now moving faster than before because they've gained energy, right? Next, explain in terms of the particles of the gas why the pressure of the gas exerts on the walls of the metal cylinder increases as the temperature increases. It's also a simple question. Okay, if this is the case, right? Now, as the case increases, as the temperature increases, why does the pressure increase along with it? Well, we saw now we have this is for 3 marks, so we have to provide a solid layered argument one by one. So we'll say, well, the particles they move more as the particles get heated up. Gas particles. I'll write in form of points with arrows, right? So you can frame the argument by yourself. Gas particles move vigorously, collide with each other, and walls of container more frequently, right? So as they are hitting each other and colliding with the walls of the container more frequently, what happens is uh, more frequently and with more force, so hence अभी यहाँ पर if there's a we know that pressure is equal to force per unit meter, right? So if the force with which the particles are colliding the surface of the metal increases, of course, pressure also increases, right? So pressure increases with the force of collision. Pressure increases due to the force of collision. So this is a sort of layered argument. I hope you can write it. Of course, you don't have to write the answer this way, but you have to write in the form of structured sentences. Okay, this is just a mental map of the question. The gas in the cylinder reaches a temperature of 100 degrees centigrade. The piston is released. So finally, we're moving the piston. Okay? Because previously we saw that we will not move the piston, right? Previously we said we're not moving the piston, but we're heating up the gas. So of course the pressure inside builds up. But now we're moving the piston. The piston is released. If you release the piston, of course, it's going to move upwards because there's a lot of pressure in the gas. To the piston, let's say previously it was here, now it's going to move somewhere over here. Piston sort of moved, piston is released and it moves upwards. Okay, so previously it was here, and now previously it was at the dotted position, and now it has moved upwards by this height. Right. The pressure remains at the temperature remains at 100 degrees centigrade. The pressure of the gas, well, the temperature remained at 100 degrees centigrade. The pressure of the gas now decreases. Explain in terms of the particles of the gas why the pressure of the gas now decreases. Now, this is a pretty simple and non-intuitive, sorry, very intuitive and a common sense idea that we know that the pressure is equal to force per unit area, right? So if you notice, area was just this before, at which the collisions were happening. But now the area has significantly increased, right? Because we've raised the piston. Now the area at which the particles are doing the collision has significantly increased. So if you look at the proportion, when area increases, the pressure should go down. Okay. So verbally, how would you say? The molecules have now more surface area to collide. Right? So more surface area means more, since more area is inversely proportional to the pressure, so the pressure decreases. Okay. I hope there's no confusion about that. So how would you write this? The particles, because the particles now have more space, right? So the particles now have now moved further apart. Particles have now moved further apart, right? Increasing the, is it okay if I write surface area as SK? We do it in maths as well. A surface area
Yes.
of, increasing the surface area of the lesion. Okay. So there is less collision per meter square or whatever, per unit area. So less collision per unit area. So less collision means less pressure. Okay, therefore, less pressure. Okay, of course, I'm not writing it as formally as I should or as you should in the Cambridge exam, but I'm just trying to give you an idea what the argument for the answer looks like. Right, next. Eventually, the piston stops moving. Explain why. Well, when does motion stop? We kept the piston as fixed, and then we released the fixed piston, and the piston has now at this point. Right? Now, why did the piston stop moving? The piston stops moving because whenever there is a balance of pressure on both sides. So we know that externally it is impacted by the atmospheric pressure. So we have external atmospheric pressure of, normally the external atmospheric pressure has a certain value. It has a almost fixed value, almost a little more than 100 kilopascal. Maybe in fact, I think it's 1.325 kilopascal, but let's just say it's a 100 kilopascal. Now, external pressure that is being applied is 100, almost 100 pascal, right? So the piston will only stop moving almost 100 kilopascal. The piston will only stop moving if there is a counter pressure of 100 kilopascal. If those two pressures balance out each other, only then, what does it mean? That's fine, better. Okay. So 100 kilopascal means If the pressure, the outward pressure, the pressure from the outside and the pressure from the inside is balanced, well, the piston will stop moving. Piston will only move in the direction of the higher pressure. If the external pressure is higher, the piston is going to move inwards. If the inward pressure or the internal pressure is high, then the piston is going to move outwards. But when the both pressures are balanced, that's when the piston would stop moving. Yeah? So there is no resultant force with resultant pressure. I would say there is no resultant force. I would say that the atmospheric pressure, and not yet, I just say the external pressure. That's more safe. The more general, the safer it is. The external pressure is balanced by, mind my handwriting, um, is balanced by the internal pressure. So no net movement. I'm very sure you can write it better than this. I'm just written it very roughly just to give you the idea. All right, on to question number 4. All hands on question number 4. A student directs a beam of white light from a filament lamp. So we know that white line is actually there's a bunch of lights together, right? A lot of lights, they add up together to form a white line. And you pass it through a prism, the line breaks down into different components. A student directs a beam of white light from a filament lamp towards a glass prism in a dark room. Figure 4 shows the weight of the a screen is incident light on the left hand side of the glass prism. Okay. Screen is placed on the right of the glass prism. So we have a screen. Red light is observed. So here is the red light. Point R on the screen. The violet is observed at point V. So violet is here. I hope you've remembered in kindergarten. I'm sure you've remembered the rainbow colors, right? B, I, B, G, R. Violet, indigo, blue, red, green, yellow, orange. So here's V and here's R. So all the colors are in between. Right. Draw on figure 4.1. Show the path of the red light and the violet light between the left-hand side of the prism on the screen for Acha. Now, what we're supposed to do over here is we have to, because there is a disconnect. You see, the line is entering, but we do not see a line passing through the prism. We do not see the line refracting and entering there. That's what we have to draw. This is exactly what is being asked over here. As well, draw on figure 4.1 to show the path of the red light. So we are supposed to show the path of the red light and the violet light. So we have to show the path for the violet light as well between the left-hand side of the prism and the screen, the point R and Y. Anyway, so this is the left side of the left-hand side of the prism. Yes. We know that this is a very high frequency light. Violet is, I mean, after that it's ultraviolet, right? So this must be a very high frequency light. And infrared, after infrared, after red, we have infrared, which is a pretty mellow and low frequency and bigger wavelength light. So, which means violet among the colors, among the visible lights, violet has the highest frequency and the smallest wavelength. So anything that has a highest frequency will do more bending, as you can see over here as well, right? Because this is the incident ray, and this is how far it has bended. So what I'll do over here is I will first of all draw. So here's the normal. This is the normal perpendicular to the surface. I think this will be normal. Yeah, this would be the normal. So it bends towards the normal, right? Something like this. And then here's the normal again. So the light will bend towards point R. But you notice this is not a lot of bending. It almost looks like as if it's a straight line. There is bending, yes, but not a lot of bending. Because red light, it has less frequency and it's less energetic compared to violet. Violet has a lot of energy, well, not a lot, but yeah, still a lot of energy and smaller wavelength. They're actually high frequency light waves. So the light enters from here. Now, if you notice, we have more bending. And also over here as well, we have more light, right? So, yep, there we go. Please draw the lines. All right, next. So we did this, it was for 2 marks. We only have to draw two ways. State what these observations show about the change in the speed of light. Well, the diffraction is happening over here. And how did we define diffraction? Well, the way we defined diffraction is change in the speed of wave, right? The diffraction could be in sound waves, the diffraction could be any types of wave, right? So, yeah. So diffraction is when, how would you define diffraction is when the speed changes. Speed changes with medium. As you change the medium, the speed of the wave will change. So what happens, what these observations show about the changing speed of red light and the changing speed of the violet light as it enters. So of course, violet has a lot of energy, right? So more energy, more frequency means a lot more change in speed. While red, we don't have a lot of energy. The deflection is also not that much. So the change in speed would also be less. Uh, about the change in speed, yeah. So we're supposed to find out about the change in speed. Okay. Right. So first of all, the both of them they travel slowly because air glass is the denser medium. Right? This glass is a denser medium. You agree with that? We have air outside, it is far lighter than the glass. So glass is a denser medium. So light, in fact, is entering the denser medium. What happens when light enters a denser medium? It slows down. Whether it's a blue light, whether it's a red light, it will slow down. Okay, so I'll say, well, both the lights, both the red and violet, lights slow down as they enter the glass medium. Okay, and then enter the glass, I would say, or you can write it in brackets in the tensor medium. Okay, so that's the first thing to know. Well, what's the second thing to know? Where is this change of speed more? In other words, which ray changes speed more than the another? Well, red light changes speed. The change of speed for the red light is less as compared to the change of speed for the blue light. In other words, um, can I say the red light? So the change of speed for the red light is slow, which means the red light moves faster through the through the glass as compared to the violet light because there's a lot of change of speed, so it's going to be slow. And we know that light slows down when it enters the denser medium. So it's the red travels faster as compared to the blue or the violet light. Straight. Then violet. Okay. Still, I may not have written so well, but I'm counting on you to do that. 5 other colors of light appear on the screen between the red light at point R and the violet light at point V. Of course, we know that with cure all the colors of rainbow. State the names of the 5 colors and list them on correct order from red to violet. Okay, so we know what we know is Vibgyor. Right now, red is at the beginning, which means we have to start from red, and violet is at the beginning. So we have to go backwards on the curve. So R comes first, then comes orange. After orange, we have yellow. After yellow, we have green. So red, orange, yellow, green. Red, yellow, sorry, orange, yellow, green, blue, indigo. And by the very end, we have violet. Right? This should be simple. State how the frequency and the wavelength of the colored light change going from the red light to black. Now, this is the frequency change. Think about it carefully. I think we've discussed this before. As the light is traveling, but in whatever circumstances, there's frequency change. We know the frequency only depends on the source and it does not change. Frequency Frequency does not change. Why is that? Because, well, it depends on source. And the wavelength, well, we're going from violet to red, red to violet. So we're moving towards high frequency. So when the frequency is high, it's like this. The wavelength gets really, really shrunk. So the wavelength becomes smaller. So wavelength decreases, also. Okay. Hmm. Wavelength, it does not change. Wavelength decreases. Right. On figure 4.1, point P is immediately next to R. So between red and ultraviolet, with this addition point, which is P. What should it represent? What do you think? We have all of the VIBGYOR, V, I, B, G, Y, O, R. We have all the VIBGYOR in between the R and V. Right? What is beyond? Can you predict? We know that after V, we have UV, ultraviolet. Right? So before R, we have infrared. This is also not quite safe. No, I'm sorry. In fact, infrared, UV is not quite safe. Infrared is emitted by heating substances, so it should be fine. Right. State which region of electromagnetic spectrum is detected at point P. Well, it is infrared. And normally, the way we experience infrared is through heat. You may not see infrared, right? But the way we experience it is through heat. So which region of electromagnetic spectrum is designed for? Is detected at point P. It's actually infrared, and for some reason I'm sleepy. Yeah. So we're done with question number 4. Question number 5 says ultrasound is a longitudinal wave which cannot be heard by humans as the frequency of the ultrasound is too high. So ultrasound, is a longitudinal wave. They cannot travel in a vacuum. Why? Because it's not electromagnetic wave. Only electromagnetic waves can travel through a vacuum because sound, even though it's ultrasound, sound requires the back and forth of the particles of the medium. Well, in vacuum, we do not have any medium. So the particle vibration cannot take place. And if the particle vibration cannot take place, the compressions and the rarefactions will also not happen. And if they won't happen, then the sound or the other sound will not be able to travel. Right? So explain why ultrasound cannot travel. Well, we'll say ultrasound is transmitted by vibrating matter. The particles need to be vibrated. Ultra Sound travels by ultrasound travels by uh, motion of the vibration of the particles of the medium. Vibration of medium particles. Yeah, I think this should be enough because we'll say, well, vacuum, since vacuum does not have any particles, this is why it's a vacuum. Doesn't have particles, so no ultrasound. Sorry, my bad. I'm just sleeping tired. Explain how longitudinal wave differs from transverse wave. Oh, this is pretty simple. I'm sure you've done this a lot, so many times. In longitudinal wave, I hope you remember from the diagram. I'll show you. This is the motion of the particles, and this is the motion of the wave. Okay, this is for the transverse. When the motion of the particle is perpendicular to the direction of the propagation of the wave. While in longitudinal, you have this is the motion of the particle, and this is the wave motion. So that is longitudinal. That is for the longitudinal. Now, how do these waveforms different? How do these waves differ from each other? Right? Well, in transverse waves, the particles move perpendicular to the direction of propagation of the wave. I'll write it if it sounds like a lot. In transverse waves, particles vibrate perpendicular to the direction of the wave propagation, to the direction of wave propagation. While in longitudinal waves, the direction of particle particles vibrate parallel to the direction of wave propagation. Okay, I don't know why it took long, but I hope it I hope it's understandable. Next, ultrasound transmitter used for a medical scan produces an ultrasound wave of frequency for 8.4 megahertz. In soft human tissue, ultrasound travels at 1,500 meters per second. Calculate the wavelength of the ultrasound in soft human tissue. Well, should be simple because we know the wave equation, and that is V equals F lambda. And this is exactly, we don't even have to rearrange the equation because we already have to find out lambda. Lambda is already the subject. So, no, in fact, what? V is equal to F lambda. I'm really sleepy. So you need to find out the lambda. So lambda is equal to v over f. What is the speed? 1,500 meter per second. And frequencies 8.4 megahertz. Mega means 10 to the power what? 10 to the power 6, right? 8.4 multiplied by 10 to the power 6 hertz. So if you were to do the math on this, I think that you are going to get somewhere around 1.8 multiplied by 10 to the power -. Okay, that's the weight. Right. Let's see. Right. 8.4. Okay. Yeah. The ultrasound wave passes from the soft tissue into the bone where the speed of the ultrasound wave is greater than 1,500 meters per second. I see. So, of course, in entering into a denser medium, so the more dense the medium is, the easier it is for the sound to travel. The ultrasound wave passes from the top of soft tissue into the bone, where the speed of the ultrasound wave is greater than 1,500 meters per second. See what happens to the frequency. The frequency does not change. We know this, right? Frequency doesn't change. Right. The wavelength, yes. Why does the frequency not change? Well, it depends on the source. That's why. The wavelength, what should happen to the wavelength? What do you think? Let's say, well, let's look at V is equal to F lambda, right? The frequency is constant, right? We're keeping frequency and we're increasing the speed. Right? So what do you think should happen to wavelength as well? Are they directly proportional or are they're directly proportional, right? So this is constant. So which means this lambda is also directly proportional. So increases. There we go. Next. The next question says a bar magnet, here's a bar magnet, can rotate freely around a thin rod in its center. So if we have a thin rod in its center, which means this is actually pivot. I mean, it could be, it could not be, let's say. Okay, a bar magnet is at rest on a frictionless horizontal surface in a laboratory and is shielded from Earth's magnetic field. See, Earth has a magnetic field and it affects whatever is, it affects every magnet on the Earth. For example, you want to detect something with your compass, you want to detect some magnetic field, but your magnet is affected by the Earth's magnetic field. Although it's still, the Earth's magnetic field is pretty weak, but still it does influence the results. Okay. So we shielded it from the Earth's magnetic field. A state of substance from which the bar magnet could be made. So if it's a bar magnet, which means it is a permanent magnet. Permanent magnet. What substance is permanent magnets made of? I think we have seen two types of substance, iron and steel. Iron is temporary, used for temporary magnetism. Well, for permanent bar magnet, we use stainless steel. We could use steel, that's fine. Right? This thin rod is perpendicular to the top and is perpendicular to the top and bottom surfaces of the bar magnet. Figure 6 shows the view from the above of a bar magnet and the north. Okay. Karna kya, what we are supposed to do over here is on figure 6.1. So this is the figure 6.1 viewed from above. It's like on a table, we have magnet on the table. Draw the pattern and the direction of the magnetic field around the bar magnet. So I think I think we should have practiced this a lot, how to draw a magnetic field. Draw a line like this over here, draw a line like this over here, draw a line like this, draw a line like this, draw a line like this, draw a line like this. If you want, you can draw one like this, but make sure to connect the poles. Make sure you do it responsibly. Okay. And then I think this should be enough, right? So
Yes.
the magnetic field lines, okay, for the direction of a magnetic field lines, they originate from the positive side and they enter into the South Pole. On the positive side, they originate from the North Pole and they enter the South, like this. Like from the North Pole, you have something like this. I don't think the shape looks exactly like this though. The shape is more of like this. Yeah, yeah, exactly. Shape is more of um, yeah, something like this. My pen is really slippery. This whole thing is really slippery. So just bear with us. Yeah, something like this. Okay, I think that's enough. Right. Magnetic field on the power magnet. Electromagnet is switched on and a strong magnetic field is created around the power magnet. So we have a power magnet and we have magnetic field lines around the power magnet. Okay. Figure 6.2 shows the direction of the strong magnetic field due to the electromagnetic is from the left to right across the page. Draw and arrows the direction of the horizontal forces that act on the poles in the power magnet. Okay. So on the North Pole and the South Pole, if the magnetic field lines are striking, then what happens is, one second. Okay, so this on the South Pole, the force is going to, because this is the South Pole, right? So the forces will look like to the left, and the force will, because you see, the magnetic field lines originate from the north, right? And this also it's also towards the north, so this they will augment each other, and the north will be on this side. Well, from the positive side, they originate from the positive. They enter the positive side, right? Negative. So the south pole. So sorry, the south pole. So this is going to look like this. Okay. In the overall force, these are the two directions of the forces. I think the meeting is about to end. I'll send you a new link. Join that link. All right. So we have a question, part C of the same question, that says an electromagnet is switched on and a strong magnetic field is created around a bar magnet. So we have a bar magnet, uh, which you saw just a while ago. We have a bar magnet placed here, just like before. But then we have another electromagnet. We're not shown the poles of the electromagnet, but we're only shown the magnetic field lines due to the bar magnet. Okay, so these magnetic field lines are due to the bar magnet, due to the electromagnet, actually. Figure 6.2 shows the direction of the strong magnetic field due to the electromagnetic is from left to right across the page. This is left and this is right, so magnetic field is going from left to right. Draw arrows on figure 6.2 to show the direction of the horizontal forces that act on the poles of the bar magnet. So we know this case, if there's a magnetic field line, and we also know that the force will be in line with the North Pole. So the force, because this is North Pole and magnetic field lines also have the same direction, so the force will be in the same direction as the North Pole when it comes to the North Pole, but the force will have a completely opposite direction when it comes to the South Pole. So this will be the direction of motion of the direction, or at least direction of the forces acting on the North and South poles, like this. All right. Now, next question is describe and explain what happens to the paramagnet when the electromagnet is switched on. So when you switch on the electromagnet, right? But
Okay, what do you think? If we have a pivot in the middle, right? And the forces are acting, one of the forces acting this way, the other way is acting this way. What do you think should happen? It looks like the bar magnet will rotate, right? Because we have a couple of forces acting at a certain distance away from the pivot. This is, by the way, this force is acting like this in the opposite direction. This is called a couple. A couple of forces acting from the pivot at a certain direction. So this will cause rotation in. Can you predict the direction? Will it be clockwise or will it be anti-clockwise? This will be anti-clockwise. So the bar magnet will rotate in the anti-clockwise direction. Now, if the the bar will rotate in the anti-clockwise direction, it's going to keep on rotating until it becomes something like this, horizontal. It reaches a horizontal position. Now, what do you think should happen when it reaches the horizontal position? Do you have a north pole over here? Do you have a south pole over here? What happens is that the force acting on the north pole will still be in this direction, in the line of in the direction of the magnetic field, and the force acting on the south pole will still be in the opposite direction. But now these two forces will now balance out each other. Okay? So it will keep on rotating until it reaches a horizontal position, and after that it does not move. Okay, because the forces have now over here forces are creating, these two forces are creating a sort of a turning effect, but now over here the forces have balanced each other out, so this bar will come to a rest. Okay, so we have this is for 3 marks. Let's explain this. The first point I will say, well, the forces produce the opposite forces in opposite direction. Forces in opposite direction produce or generate a turning effect. Okay. And once they create a turning effect, what happens is that the magnet rotates in clockwise direction. Bar magnet, to be precise, we're talking about the bar magnet. So the bar magnet rotates about the pivot. We have to make sure that it's rotating about the pivot. Rotates about the pivot in the clockwise, anti-clockwise direction, actually. About the pivot in the anti-clockwise direction. I hope it's fine if I'm writing ACW as anti-clockwise direction. Okay, and then when it reaches a point where, and until it becomes horizontal, until it becomes horizontal, and the forces balance out each other. Horizontal position, and the forces balance out each other. Okay, so no motion. Okay. I think you can. I hope it makes sense. I think you can write it in a better form. Right, next. This is really, really simple. A filament lamp connected to 12-volt power supply and transfers 24 watt of power. Calculate the current in the lamp. Of course, it's pretty simple. We know that power is equal to VI. We know the power. Power is 24. Voltage is 12. There is I. I should be equal to 24 over 12. And I is equal to 2 amps. So the current should be equal to 2 amperes. I don't think there's anything simpler than this. The resistance of the lamp in the circuit. Now you can do it by 2 ways. You can also use the Ohm's law over here. V is equal to IR. V equals IR. So R is equal to V upon I. We know that voltage is 12. I is 2, which is the current. So this will be 6 ohms. 6 ohms. You can also do it this way. P is equal to, remember the 3 formulas of power? P is equal to I or VI and VI and I square R and I square R. And the third formula is V square upon R. So you can pick and choose the formula depending on your needs. So for resistance, I can also choose the formula, this one. Okay, P equals I square R, I'll get the same result. I'm going to show you. Okay. P equals I square R. Power is equal to 24 watts. I square would be, current is 2, so it'll be 2 squared R. 24 divided by 2 square is 4. 24 divided by 4, we know that it's 6. So R is going to be 6 ohms. We get the same result no matter which formula do we use. All right. Next, a student has a battery of electromotive force, EMF. Now, I think we've talked about this before. EMF, although it looks like a force, it is not a force. It's actually voltage of the battery. It's some of the all the energy provided by the battery to a 1 coulomb of charge is actually the EMF. The student uses a battery, the battery in circuit with 12 volt. The student uses the battery in a circuit with 12-volt filament lamp to obtain a range of suitable readings. This is important, a range of suitable readings, and plots the current voltage graph for the lamp. So we need to plot a current voltage graph, which means we need voltage. We need to make a table whereby we have voltage and we have current, and we need to have the voltage for different values of current. Of course, we don't have to do that, but we'll have to draw the apparatus whereby we are capable to do that. So how would we do this? Well, we should be able to, because we're constantly measuring the voltage and the current. So we need two devices. We need ammeter and voltmeter to be able to measure the voltage and current. Okay. And we also know that ammeter is connected in series. So we need ammeter, okay, to measure current. And we need voltmeter to measure voltage. And we know that ammeter is connected in series with the circuit and voltmeter is connected in parallel. And we need to obtain a range of values for the lamp, which means voltmeter will be connected with the to the lamp in parallel. Right? And then we need an ammeter for the current around the circuit. Ammeter is connected in series. You can draw it like this, and there is your ammeter. Now, there's one more thing I need to put in, and that is, if you notice, we need a range of values, suitable readings. Now, we're not going to get a range here. If we were to connect the circuit like this, we're not going to get a range here because a fixed amount of current will flow, this will be a fixed current, and the fixed amount of voltage will be dissipated at this bulb. And this is going to be a steady current and steady value of voltage. How are we going to get a range? We need to have different voltages across this lamp. How do you think you can obtain that? The bulb has a fixed voltage. The bulb has a fixed voltage of 12 volts. So is there a way we can get different voltages across this lamp? Yes. And that is, if you were to attach a variable resistor across it. But a variable, if you can adjust the values of this variable resistor. So the voltage across this variable resistor and the voltage across will keep on changing. So once this value keeps on changing, you get a range of values. Right? So this is pretty obvious that we have to apply an ammeter and voltmeter, but this is a little and less obvious. We have to apply a rheostat or a variable resistor, just so that we can get a range of values, different values across the bulb. So this is variable resistor. We can also call it a rheostat. And this bit is very useful when it comes to ATP, the alternative to practical bit. This bit is really useful. And you should be able to know that, you should be able to realize that whenever we are required to have a range, whenever we want to have a range, we need to put in variable resistors so that we can get a range of values of voltages across the other component. Okay, next. So complete the circuit. This is what just we did. Next, draw the shape of the current voltage graph for the filament lamp. So what happens if, I hope you remember, we talked about 3 non-ohmic conductors. We talked about a diode, when we talked about non-ohmic conductors, we talked about filament lamp, and we talked about the thermistor. A filament lamp is, and if you have a VI graph, so as the voltage increases, the current increases. Okay. With an increasing gradient, which means, sorry, not for the filament lamp, this is for the thermistor actually. As the temperature increases, it becomes easy for the current to flow. So more current flows as the temperature increases. This is for thermistor. For a filament lamp, it is the opposite. As the temperature increases, it becomes difficult for the current to flow. And we'll give a reason in a while. So the voltage has a decreasing gradient, like this. Like for diode, it's like this. Initially, there's no current, but after it hits the knee voltage, then the current just it acts like a regular. It acts like a regular conductor. So diode is not very concerned right now. I want you to be able to I want you to be able to differentiate between the filament lamp and the thermistor. So what the basic difference is, as you increase the temperature, thermistor gets happy. As you increase the temperature, filament lamp gets angry. So it becomes difficult for the current to flow. Well, in the thermistor, if you increase the temperature, it's easier for the current to flow. So we are supposed to draw for the filament lamp. Well, filament lamp, it's gonna look, you draw with the decreasing gradient, so it's gonna look like something like this. Okay? We should be fine. Do not make the graph straight from here. Do not just draw it this way. Decreasing gradient, but do not make it horizontal. Clear? Yep, there's that. Next, say what happens to the resistance of the filament lamp. Now, here comes the reason. Why does that happen? Why does the graph bends towards the voltage instead of bending towards the, if it were thermistor, it would have bended towards the current. But why does the graph bends towards the voltage in a filament lamp? Explain one reason for this happen. Okay, so what happens is in a filament lamp, if you increase the temperature, the particles vibrate more and more. Okay. We know that the flow of the electric current happens due to the flow of electrons. So if the particles vibrate more and more, it becomes difficult for the electrons to flow in a streamline motion. Okay, because due to constant collision, there are traffic jams. There are constantly traffic jams by the collision. And as the temperature increases, the traffic jams increase for the flow of the current. So even if you keep on increasing the voltage, the current will not increase as much. You see the voltage is kept on, we keep on increasing the voltage, but the current is not. If it were a fair relationship between the voltage and the current, it would have looked like this, a straight line, right? But this is not a fair relationship because this is a thermistor. So if you increase the temperature, the current will have a hard time. Current does not increase as much. Current will have a hard time flowing. Okay, so let's describe this over here. What happens to the resistance? If the resistance of the filament lamp increases, the resistance increases. The reason being, as temp increases, more vibration. So when there is more vibration, it becomes difficult for the electrons to flow. Difficult for the current to flow. So resistance increases, and therefore the current. I mean, I started with resistance decreases, so I don't think you should put in resistance decreases. I should just say, well, current decreases. Current decreases. I think this should be fine. You can form a sentence out. Question number 8. A nuclide notation for the radioactive isotope hydrogen-3 is H31. So this is one of the isotopes of hydrogen where you have, can you tell me the number of protons and neutrons in it? The atomic number is 1, which means it has 1 proton, and number of neutrons would be 3 minus 1 is equal to 2. So it has 2 neutrons and 1 protons. Explain why hydrogen-3 cannot decay by the emission of alpha particles. Why do you think alpha particle emission cannot happen on hydrogen-3? Well, if you look at the structure of alpha particles are two protons and two neutrons. If a particle, if a radioactive particle has enough protons and enough neutrons, then it can undergo alpha particle emission. But if you notice for hydrogen-3, all it has is one proton. I mean, it has two protons, but you need two protons and two neutrons. Okay? Alpha particle looks like this, 2p and 2n. Okay? It has insufficient protons to do an alpha particle emission. Okay, so we only have one proton. Okay? Alpha particle needs two proton, two neutron. Okay? Hydrogen-3 decays by the emission of beta particles to an isotope of a different element. This element is represented by the equation Q. Sorry, in the equation by Q. Complete the nuclide equation for the decay of hydrogen-3. So this is hydrogen-3. And we know that beta particle are fast-moving electrons. This is basically an electron. So electron has a charge of -1 and it has a mass of 0. So how would you balance it? I think over here it should be 2. No, over here it should be 3 actually. It should be 3 over here, and over here it should be 2 because 2 minus 1 is 1. Make sure these, if you add them up, you get this. Make sure if you add the tops, you get something that is on the top. So 3 plus 0 is 3, and minus 1 plus 2 is 1. State the name of the element represented by Q. Can you tell the name of this part? What's the identification? What's the identity mark of any element? It's not the mass number because the mass number can change, right? The identity mark of an element is its atomic number. Okay, that's how you identify an element. This is the identity mark of an element. Okay. So what, and you're only going to find one element that has an atomic number of 2. There's only one element of periodic table that has a atomic number of 2, and that is helium. And because only helium has 2 protons. So that's helium. Yes, I'm sure you're familiar with the helium that is 4 gamma 2, but helium 4 2, but helium 3 2 is also one of the isotopes of the helium. You can also write it as isotope of helium. Isotope of helium, that would also be found. Okay, so the half-life of hydrogen-3 is 12 years. Can you recall half-life? Half-life is when it takes, the time it takes for the radioactive sample to become half. That's the half-life. For example, if you had 100 nuclei, right? And let's say it took 50 years for the 100 nuclei to become 50 nuclei. So the time they've become exactly half. So the time it took was 50 years. So the half-life would be 50 years. Okay, can you describe in words? I think the time it takes for the sample of the time it takes for the sample of radioactive nuclei to be left to the half of its original number. I mean, yeah, there could be a better definition, but that's all I can think of right now. A sample of hydrogen-3 is placed on a laboratory bench next to a Geiger-Muller tube. This is a GM tube, which tells you about how much radiation is going on. It's a counter, GM cube and a counter. The count rate is recorded at the same time on 4 successive days. Now, if you think about it for a while, we are judging them on the basis of just 4 days. while the half-life is 12 years. So 4 days is peanuts as compared when it comes to uh, 12 years. Right? So if it takes 12 years for the radioactive sample to become half, do you think you'll notice any results in 4 days? Of course not. Okay. For 4 days is not going to give you any any measurable result because 4 days is way too less time compared to the half-life of 12 years. Right? So if you look at the count rate is pretty random, pretty strange. 9898, it seems like it's decreasing, but then it jumps up again and then it decreases again. So this is random because we are observing on a very short time scale. So this is why we're not getting a very, I would say, consequential results over here. Okay. So why the count rate decreases and increases? Well, the time frame of observation is very small compared to the half-life. Compared to half-life. So the fluctuations that you see in time, where it seems like count rate is increasing, although it should be decreasing throughout, but the fact that it's increasing and decreasing is due to the sheer randomness of the process. The radioactive process is very, very random. If you observe it on a very, very small scale, it's going to be very, very random. Only in the scale of a half-life, you're going to see some results. Okay, so compared to the half-life, so because we're zooming into a very narrow and short time frame, so that's why we're going to see a lot of errors. So the results, so the fluctuation in the result, let's say that. So the fluctuation in the result is due to the randomness of radioactivity. I would say that radioactivity. Radioactivity is a very random process. And we saw that in the properties of the radioactive process, spontaneous and it's very, very random. Again, okay. Question 9, the last, I think Tizia's favorite bit. A stable star in the distant galaxy has a mass that is more than 15 times the mass. So this is a pretty big star. Okay, this is one of the massive stars. Okay. State the name of the nuclear reaction that occurs at the center of the star and describe this nuclear reaction. So what is the nuclear reaction that occurs at the center of the sun? At the core of the star, we know that it is a nuclear fusion. Nuclear fusion. And what happens in a nuclear fusion? Well, hydrogen nuclei bond fuse together to form helium nucleus. I hope you remember nuclear fusion, accompanied by a huge release, huge amount of, huge, a lot of release of energy, accompanied by a huge release of energy. Okay. Right. So that's the nuclear fusion. Explain how this reaction helps to keep the star stable. Well, if you remember, there is a stable phase of the star, which goes on for millions of years, right? What keeps a star stable? Well, we know that there is immense gravity in the star, and it's constantly crushing the particles together. So if you look at this star, there's gravity that is crushing it inwards. But counter to gravity, opposite to gravity, we have an outward force due to nuclear fusion. Okay? So when the inward gravity is balanced by the outward pressure exerted by the nuclear reactions. So when they're balanced against each other, this is when the star is stable. It's going to keep on being stable until it runs out of the fuel, which is the hydrogen, and when the outward pressure dominates. Okay. So how this nuclear reaction helps to keep the star stable? Well, the energy from nuclear fusion exerts an outward pressure, okay, which counteracts the inward pressure of the gravity, inward force, inward gravitational pressure. I would just say that. Gravitational pressure, keeping the star stable. Right? Yeah. Okay. As a massive star approaches the end of its life, it stops being stable. So what happened to the stability? We saw that there is outer pressure and the inward pressure by the gravity that is keeping the star stable. And it becomes a red supergiant. Remember, we're talking about a massive star. Only a massive star becomes a red supergiant. State why the nuclear reaction can no longer keep the star stable. Well, the fuel for the nuclear reaction is hydrogen. Okay? So when the star begins to run out of hydrogen, that's when the nuclear reaction stops, or the rate of the nuclear reaction decreases, and the inward pressure dominates. The inward gravitational pressure dominates. Can no longer keep a star stable? Well, because the star runs out of the fuel for nuclear fusion. What's the fuel for hydrogen? Okay. So the inward pressure dominates. Inward pressure dominates. This should be the last question, I think. Yep, this is the last question. Describe what happens to the red supergiant. And this is for 3 marks. So, yes, anybody can tell. So, in a red supergiant, what happens is it goes through, of course, the inward pressure keeps on increasing. It pressures the star, and there's an inward explosion. Okay, the heavier atoms become the heavier atoms. Atoms heavier than iron are thrown out into the outer space, not the outer space, thrown out of the star, forming a supernova. And after supernova, it either becomes a neutron star or not. Maybe let's try this. So what happens to the star? Well, it forms, it explodes, first of all. First thing that happens, it explodes. Yeah. Should it begin with explodes? I think it should begin with inward pressure. Heats up the star. Heats up the star. I would say the core of the star, not the star. All of the star heats up the core of the star so much that it explodes. So what happens after it explodes? Well, supernova. Okay, this explosion is supernova. Okay. And throws out heavier metals. This is what the job of the supernova. Throws out heavier elements, I would say, not necessarily metals, and forms a planetary nebula. Elements. Leftovers are nebula. Supernova, the remains or the ashes of the supernova is actually the nebula, which becomes the raw material for the next star. Okay? For the with a new star. So it's a cyclical process. And well, how does it end up? It ends up being the core of the star. Core of the star either becomes a black hole, or a neutron star. Okay, yeah, that's pretty roughly written, but I hope you get the idea. Okay, so this was all of our paper 2 variant 1 of 9054 October November 2024.